Welcome everyone, my name is Moritz. I'm a developer relations engineer at Dfinity. I've been active in the Dfinity community since early 2018 and I'm really happy to participate in the Motoko Bootcamp as a mentor. And what I'm talking about today are HTTPS outcalls. Please note that I use HTTPS and HTTP outcalls interchangeably, as HTTP is way easier to pronounce for me than HTTPS. So with that out of the way, let's find out what HTTP outcalls actually are. Put simply, HTTP outcalls allow smart contracts to directly make HTTP requests to external Web 2.0 servers. So before we understand why this is awesome, we're going to take a look at how things used to work. In general, blockchains until now were isolated entities, and smart contracts couldn't directly communicate with other blockchains or external servers. And the reason for that is that blockchains are replicated state machines, and each replica has to perform the same computations on the same state to make the same transition every round. And doing computations based on results from external services as input can easily lead to state divergence if done in a naive manner. So let's look at two examples. What you see here are two state machines, one at the top and one at the bottom. And they have two states, 1 and 2, and two possible inputs, A and B. And we imagine the inputs A and B are the only possible responses from a server, maybe the Coinbase API, for example. And that the two state machines actually represent a node in the network. Like each of them represents a node in the network. And we now imagine the nodes had to perform a computation based on a response from the server because a canister in their subnet requested information from it. So what would happen is that both nodes would call the API and both would receive a response from it. If the response is the same, for example, A, then both nodes end up in the same state. So imagine we begin here, state 1. Both of our replicas receive a response from the server, which in both cases is A, so they both end up in the same state, which is state 2. But if we now imagine that the server actually returned a different response for each of the replicas, so A for the first one and B for the second one, they would end up in different states and couldn't reach consensus on their state. So if we are in state 1 and receive A as an input, we end up in state 2. And if we are in state 1 and receive B as input, we end up in state 1. And the likelihood that this actually happens is pretty big, as we see in a second. So the likelihood that the server returns two different responses if requested by two different replicas. So let's look at some examples of responses from a simple weather API, for example. So in this scenario, each node makes the exact same call to the weather API. And in the first case we are examining, all the responses are equal. So in this case, nodes won't have a problem in reaching consensus as they all perform computation on the same state. And please note that I might use node and replica interchangeably throughout the video. To be precise, a node is the actual physical hardware and a replica is the software run on the node. In our second example, some responses could be different. And this can be either due to the Web 2.0 server being called responding differently, or due to nodes being compromised and falsifying the received correct response. As long as less than 1/3 of the responses are different, the consensus protocol is taking care of the subset of deviating responses and goes with the majority of the replicas. Now let's look at the most general case, and that is that each response returned by the server is different due to the variable parts being contained therein. And this could be because of a timestamp included in the response, because not all requests are sent or handled at the exact same time. Maybe also some unique identifiers or just a different ordering of the response from the server. And in this case, the replicas are not able to agree on a single response value as part of the consensus, and the state machine cannot progress to the next round. So we need to somehow transform the responses so that they are all identical, and we will get back to that later in the presentation. So previously, people used oracles to solve this problem. And this usually involves trusting an entity to provide a smart contract with external data. And this data can then be consumed by other smart contracts. And the problem is that these services must be trusted to be honest and not get hacked or otherwise become faulty, and also be paid. And moreover, they cannot help when smart contracts need to interact with off-chain services, for example, by calling into a web-based API. They usually can only provide off-chain data. So let's take a look at how oracles work in detail. For this comic, the white box is the on-chain world, and everything outside of the box is the off-chain world. And the flow begins by a dApp's smart contract making a request to the Oracle smart contract on-chain. They could, for example, ask the Oracle smart contract for the current price of ICP. This request is then stored temporarily by the Oracle smart contract. And an Oracle, so for example a Web2 server, then obtains the stored request from the Oracle smart contract through regular ways of interacting with it. It then executes the request in the Web2 world, so in this case by, for example, calling the Coinbase API using a regular HTTP call. And the Oracle then receives the response from the target server. It provides the response back to the Oracle smart contract, again using the normal interaction paradigm of the blockchain. And finally, the Oracle smart contract provides back the response to the calling smart contract using a standard on-chain interaction. So now that we know how things used to work, let's take a look at what HTTP outcalls enable. As mentioned a bit earlier, HTTP outcalls on the internet computer enable smart contracts to directly make calls to HTTP servers external to the blockchain and use the response in further processing of the smart contract such that the replicated state can safely be updated using those inputs. In simple terms, this means that we do not have to rely on oracles to obtain external data and that we can actually interact with the off-chain world. So what are advantages of this over the Oracle model? The first one is a stronger trust model. So canister HTTP outcalls require no external intermediaries or oracles for smart contracts to communicate with external servers. We also have lower fees because there are no intermediaries in place to charge additional fees for their services. And we are also closer to the standard programming paradigm, because the paradigm of a smart contract directly making HTTP requests to external servers is much closer to the normal programming paradigm that engineers are used to when you compare it to using oracles. And this abstracts the fact that you are programming for a blockchain further away, which is pretty nice. So why is this important? There are a couple of reasons. The first one is that most real-world dApp use cases need some form of data exchange with off-chain entities. And most of the world's data is currently held on traditional services, and many dApps build on this data and therefore need access to it. Also, in order to be able to reach blockchain singularity, smart contracts need to be able to interact with Web2 services. So let's talk about how this works. The feature is implemented as part of the Internet Computer Replica, so the software that is run on nodes of the network, and is exposed as an API of the management canister. The management canister is actually just a facade and it does not really exist as a canister. So to begin the process, the dApp canister calls the HTTP request method of the management canister. The request is then stored in replicated state of the subnet. Then periodically, so each round, an adapter at the networking layer in each replica fetches the pending HTTP outcalls from replicated state, and the adapter on each replica then executes the HTTP request by sending it to the target server. The corresponding HTTP response from the server is received by the adapter on each replica of the subnet and provided to a component in the replica process. Next, an optional transformation function implemented as part of the canister, is invoked on the respective response on each replica. This transformation is what allows us to make all the responses the same, for example by removing timestamps or any other variable parts. If we think back to the weather API example, our transformation function would, for example, discard everything in the response except for the actual weather conditions. The transformed response is then handed over to consensus on each replica, and the IC consensus agrees on a response if at least 2/3 of the replicas have the same response for the request as input. And in this case, consensus provides the response back to the management canister API, or an error if no consensus can be reached, or in case of any other problems. In the final step, the management canister API provides the response or error back to the calling canister. So to summarize, to perform an HTTP request, each replica pushes an optionally transformed instance of the received HTTP response from the external web server through the internet computer's consensus layer so that replicas of the subnet can agree on the response provided by the canister based on all the server responses received by the replicas. The optional transformation ensures that if responses received from the server on different replicas are different in some parts, that those differences are eliminated and the same transformed response is provided to consensus on every honest replica. And this guarantees that on every replica the exact same response or none at all is used for canister execution. This ensures that diversion does not happen when using this feature and the replicated state machine properties of the subnet are preserved. So what are some limitations of this feature? The IC itself is an IPv6 based system. So the HTTP outcalls feature is therefore also an IPv6 only feature. But the team is already working on a solution to enable IPv4 calls as well. Another limitation is that we have to trust the HTTP service we are calling, to be honest, but this situation is the same for oracles and Web2 services as well. The next thing we have to trust is the internet computer, and we can do that if we assume that at least 2/3 of the replicas are honest. As responses are potentially subject to the same transformation function, they have to be somewhat similar in the core information we are interested in. A common setting is that responses are structurally equivalent, but certain fields differ, like a timestamp, for example. Another limitation is that post requests must be idempotent. And this means that the receiving server should not execute the same post request multiple times. Think of adding a piece of data to a database. If all nodes in the subnet send the same request to the database, it would be bad if you add the piece of data many times instead of only once as intended. And this can be mitigated by using an idempotency key in the request, which is a unique random string allowing the server to identify all but one request as duplicates. A problem here could be that A, the request that is being processed by the server was tampered with by a malicious replica, or B, a malicious replica actually changes the idempotency key, leading to its request and the actual intended request to be processed. Also, not all APIs support idempotency keys, so Dfinity decided to work on a reduced quorum feature, and this would allow the canister to set the quorum size to 1, leading to only one replica to execute a post request. As we already hinted, compromised replicas are a problem in general, because they could make arbitrary post requests that the canister is not even aware about to the server. For example, if there is a key or a password stored for authenticating to the external server, a compromised replica could use the stored plaintext credentials to authenticate to a server without our knowledge. But this problem cannot easily be solved with oracles either. So one example, though, of securing the right integration is to sign post requests with a subnet signature using chain key cryptography, and then to have the server check the signature. This approach requires adaptation of the server, but it actually solves the problem of dishonest replicas making arbitrary requests. Another problem is that most APIs have rate limits. So once the quota for an IP address is used up, requests from the prefix would not be served anymore. And the problem is that all canisters on the subnet share the IPv6 prefixes of the replica of the subnet, and thus the quota at each server that implements rate limiting. And as every replica makes the same request, the quota can be consumed quickly and replicas temporarily be blocked. API keys could actually solve this issue, but then we have to consider the possibility of compromised replicas that we discussed earlier. Right. That was it. So now if anyone has any questions, yeah, raise your hand or... Okay, I think Ahmed wants to ask a question, right?
Did Ahmed raise his hand?
I mean, it says 30, but there are only like 4, so I thought those are the ones that already raised their hands.
No, it says well simple. Anyone have any questions?
So either it was crazy confusing for everyone or it was really good. There's no in between.
All right.
He shows the code. Yeah, we'll get to a code example after the Q&A. So we have like 4 or 5 minutes of Q&A, and then after that I will show some code. The management canister. Yeah, I can talk a bit about the management canister. It's basically, like I said, like a virtual canister. I'll share my screen in a second. It basically allows you to interact with like more like system level APIs. So for example, if you want to work with the Bitcoin integration, you also make calls to the management canister, or if you want to use the HTTPS outcalls feature, you also talk to the management canister. And the management canister basically makes it easy for developers to kind of like use that functionality that's not really provided by a canister, but by the system or by the network itself. Because then you don't have to use like a library or something. You just have like the interaction paradigm that you are used to, which is basically talking to a canister. And I think that's like the reasoning behind exposing the those methods in a like virtual canister that you can then call. And if you're interested in like what this canister offers, you can head to the interface specification in the documentation. And there's like a whole section about the management canister and about like all the things that it offers. And we will actually use that in a second. So this is like the service interface of the management canister. As you can see, we could, for example, from a canister, create another canister by making a call to the management canister. You can update settings, install code, delete canisters. This is the HTTP request method that I've been talking about for this presentation. You could also make a call to basically get like a threshold ECTSA signature from the internet computer. And then you also use it to interface with the direct Bitcoin integration on a low level. Yeah, I hope that answers the question. I will answer Lee's question. So he wrote, so in summary, you allow the use of API keys or not? We definitely allow the use of API keys, but depending on like your, let's say your threat model, it's maybe not a good idea, because as you can see, there were in the presentation, there are like some issues of like storing API keys in a canister, because we are in a decentralized network, we can't really assume that every participant in this network is like a good actor. Like we also have to consider the fact that there are some nefarious actors in our system. And those bad actors could then
if you stored plain API keys in the canister, they could then basically take those API keys and like authenticate themselves to the server you were supposed to call from your canister without you even noticing. So they basically take out the API key out of the canister, and then like on their own server, they just constantly like make calls to that server, pretending that they are you. So in general, if there's like a security concern about this, and Lee just wrote a comment, but to quote, but most Web2 providers limit requests by using keys. How then work around this? Yeah, that's a good question. So like one idea that you can do is that you basically set up your own server, and your own server only accepts calls like HTTP outcalls from your canister. So you could either verify that by looking at the signature of the, you probably need to verify that using what I just said on the last slide. You threshold sign the request to your server, and that way you know that it's not like one single server trying to nefariously make you do something, but you know that actually the entire subnet agreed that this is a valid call, in a sense. And then what you do after, like on your server, if you receive like a request, you basically check that the threshold ECDSA signature is valid. And if that's the case, you then make on behalf of the canister a call to the API that is like behind, or that you only can access if you have like API keys to interact with it. I hope that made sense. All right, so this is done. This is also done. Is it possible, Takao asked, is it possible to use the put method? Yes, it's definitely possible. You can use the put method as well to make HTTP outcalls. You can also write to external servers. So do we have any other questions, maybe? Right, I guess not. Oh, let me actually check, like someone raised his hand, right? How do I do it when the screen is shared?
Yeah, let's see. All right, we've got Vishnu, Karma. You're
Okay.
allowed to speak now.
Hello,
Hello.
am I audible?
Yes, I can hear you.
I have a question regarding to your boundary nodes.
Yeah.
So, load balancing among the subnet replica nodes. If a replica is lagging behind and has already a lot of work on its plate, I am confusing about it.
I think you cut out in the end.
Yeah.
I mean, I understood you, and I understood you until you said if a replica has a lot of work on its plate already, and then after that, what was the continuation?
Boundary node will send the request to another replica.
Is that like, do you want to ask if that's the case, or?
Yeah. Can you explain it simply?
I mean, I'm not really an expert in boundary nodes, but my understanding is that when you make an HTTP request and that lands on the boundary node, the boundary node basically.
Yeah, it convert in canister call.
Yeah, I think it's like randomly choosing one of the nodes in the subnet that's answering your request. Yeah, but I'm currently talking about query calls. I don't know if that's what you also intended.
Yeah.
Okay.
Okay.
If this doesn't answer the question, maybe like, I don't know, if you're really interested in the details, you can make like a post on the forum, and then I'm sure like some boundary node experts will get back to you.
Okay, okay. Thanks.
Yeah, thank you for asking. All right. And Tom asked, what is a typical delay, so time difference between canisters making the same outcall to the Web2 server? So what do you mean, like between canisters? Usually it's like one canister making the outcall, and then the replicas on the subnet, so basically the servers that make up the subnet, pick up that request, and they all send out the request to the server that the canister specified. So maybe that's what you're asking. And if that's the case, if that's your question, otherwise you can also raise your hand, and then I will unmute you. There you are. Okay, you should be allowed to talk now.
Yeah, what I meant was, maybe I haven't truly understood, but the same code is run by all the different nodes,
Yeah.
or replicas in a subnet.
Yeah.
So if one of the canisters, if one of the replicas has a canister making an outcall, I'm assuming that the other replicas are going to do the same.
Yes.
Yeah. So what is a typical time delay or time difference between, say, for example, we have 3 replicas, A, B, and C. What would a typical sort of time difference between A and B and C executing the same code?
That's a good question. I don't really have any numbers on that, so I can just like estimate. So I'm not sure if it's true what I'm saying, but I would guess it could differ at least by a couple hundred milliseconds, because like the replicas, like what we are trying to do when we basically allocate nodes that run a subnet is that they are like in different geographies. So for example, that not all of the 13 subnets are in Berlin, Germany, in the same data center. We try to like decentralize that, so that maybe like one is in Asia, the other's like in Africa, one in Europe, and so on. So depending on where the target servers that you are calling, if the server would be, for example, in Berlin, and the replica that sends the outcall is in Berlin as well, maybe even in the same data center, then the response time should be like really, really fast. But if another node in the subnet is on the other side of the world, and it has to like talk to the HTTP server in Berlin, it takes way longer for the request to get there and then also to come back. So yeah, I would expect that there are could be a couple of hundred milliseconds between those replicas receiving the answers, or until the server receives the request from the replica.
So if we have very time sensitive data, there's a big possibility of consensus not being achieved.
That's actually what the transform function is for. So this thing here, like, I don't know if you talk about the same thing, but if you're thinking that you cannot reach consensus because, for example, there's like a date field in the headers, and that's like different from node to node, that's actually what the transform function is for. So what it does is, like, on each replica, you call this transformation function. It takes the HTTP response from the server, and then it strips out all variable parts. So for example, like a date stamp, and it provides only like the true clear information that should be the same no matter which replica made the HTTP call to consensus. And then if 2/3 agree, yeah.
Yeah, no, I get that, but what I'm getting at is, if you're calling a target server and the data is changing extremely quickly, it sounds like we shouldn't be using this feature in that case.
That's true, yeah. Yeah, like I said, the data kind of has to be structurally equal. I mean, you could, for example, in the transform function, I don't know if it's like if you're receiving like, I don't know if it like makes a lot of sense, but just for you to understand what you could do in the transform function, you could, if you receive like I don't know, the price for an asset with like 3 numbers after the dot, you could, for example, say, okay, within like 2 seconds, it's very likely that it changes, like the digits after the comma change. But in your transformation function, you could just strip them away and then live with less information, but making sure that the replicas receive consensus. But we will see an example of that later on. I'm going to take like one more question, because otherwise I think we run out of time and I don't want to like make this go
Thanks for that.
forever. But thanks for the question.
Thank you.
Okay, so that was answered. And Oye asked, what is default timeouts connection read for outcalls? Whether implemented chunks, probably multi-parts, live states, requests. I think I kind of know what you're asking, but to be honest, I don't know. I haven't read anything about it. I don't know like how long a replica retries, or if it retries at all. Yeah, but if less than or if more than 2/3 receive a response, even though if like a couple of the replicas don't get a response back, it's still fine, because to reach consensus, we only need like 2/3 of the replicas to have the same response. I guess that's how it works, but just a guess. All right, then I would close this and start with the demo part, and then after that we can do another Q&A. So let's see. So I hope you all see my screen. And I start by talking about like what our goal is. So what we want to do in this code example is we want to leverage the new HTTP outcalls feature to make calls from a canister to the Coinbase API to get a very specific historic ICP price. And as you can see on this comic, we have like one canister. This is us calling the canister. This is the Coinbase API. And what we want to do is we want to implement a get price method on the canister that we call. Then on behalf of us, the canister makes an HTTP request to the Coinbase API. The Coinbase API returns the response and we get back the result. So, and we're actually starting this from like scratch, like completely new without anything. So the first thing we are going to do is restarting our terminal. Which is slow. I don't know why. Okay, there we are. So we're going to create a new project with the no front end flag, which basically omits like any front end part within the repository, and we are going to call it project price feed. Then we're going to go into the price feed directory, and we are going to open our favorite editor, which is Visual Studio Code. And then I have to move this bar away, which I can somehow. Okay, I'm just going to stay here. All right, the next thing we are going to do is that we're actually going to delete this front end folder that's somehow still there, even though we specified we don't want to have a front end. And we're also going to remove the front end assets canister from our canisters definition in our defects.json. And the first thing we are going to do is that we are actually defining our public method that we expose, which is the get price function. And it takes no arguments. It returns an asynchronous result, which in the case of success is going to be a text, and in the case of failure is also going to be a text. Now, they complain because we don't have results imported, which we are going to do now. And to begin, we are just going to simply return an OK that contains the text "this worked all right." So now that we already know that we have to call the management canister to make HTTP outcalls, we somehow have to find out like how to call the canister with the correct arguments. So we have to know the interface that the management canister offers. And so how do we actually get the management canisters interface and use that interface inside our code? I mean, I already kind of hinted it to you. We are going to go to the website of the interface specification. And we scroll down to the management canister. We then get like the entire interface overview as a candid file. And if you click on this underlined text, it actually downloads the interface specification. So, but that doesn't really like help us because, yeah, that's a did file. To get around that, we are going to download a tool called didc. You can get it from GitHub. It's in the candid repository. You can just go on the release page and then download the binary for your architecture. I already did that, so I'm not going to do that again to save some time. And I also already downloaded the candid interface as well. So, all right, so we have didc installed, and we have the did file of the management canister. And what didc allows us to do is that we can take any candid file and basically generate the Motoko files off of that. So that's pretty cool. So if you don't know, candid is like an interface description language for interacting with canisters running on the internet computer, and it provides a language-independent description of canister interfaces and also the data that they exchange. So, like I already mentioned, usually what you get when you like kind of wonder what interface a canister exposes is like a did file, because it's language independent. So if I write a canister, I don't have to provide like Motoko types, Rust types, maybe, I don't know, JavaScript bindings and all of that. I just provide like the did file. And then what you can do using didc is that you basically create the corresponding types to interact with that canister from the candid file. Because if you were to try and interact with the canister from just a did file that within your target language, for example, with Motoko, that wouldn't work. I can't just like import a did file into my Motoko code base, because yeah, the Motoko compiler doesn't understand what did is. So that's exactly what we are doing. We are going to, if you want to know like what this tool can do, you can just like, I don't know, write like help, and then you get like an overview of what it does. We're going to use the bind method. So if you're interested in what that does, you can also go for the help flag. And as you can see, we have to provide an input, which is our candid file. Then we have to specify a target, which is what we want to convert the did file to. We have like a couple of different values: JavaScript, TypeScript, did, Motoko, and Rust. Obviously, we're going to pick Motoko. And then we have a target, which is basically the file that we want to like save the binding into. So we are going to do, like, if you download this weird file, it actually has this long name down here. So IC dash, this is probably like a hash, .did, that we specify the output type, which is Motoko. And then we pipe the output of that into our repository, so into price feed. Then we go into source, price feed backend, and we created a new file called types.mo that like hosts all the types for our project. So let's run that. So now, as you can see, we have this beautiful file here, which now contains the Motoko types of the management canister created from the did file. And if we go down here, we again see like the service definition of that actor. So all the methods that it exposes, all the arguments that method takes, and what it returns. And what we are going to do next is that we actually rename this self to IC to make it like more clear what this actor actually is, because it's like the management canister, so kind of a way to interact with the internet computer itself. What you could like alternatively do to get to those types is to look into like examples repositories or other repositories that like need this type, and then just copy it out there. But I just wanted to show you how to do it if those like if you can't find like Motoko types for any project. So you're like, yeah, more independent. All right, and like I said, the management canister is just a facade, so it doesn't really exist. It's like a shim. And if you want to talk to the management canister, it has like a specified canister ID, which is 5As-2As. So whenever you want to like import it in your project, you have to know this canister ID, but I think it's also like specified in the interface definition. All right, so let's create a management canister actor reference. All right, so we write let's IC types dot IC. So this is the actor type that we just generated, and then we say actor from the principle that I just told you about, 5 times A, 2 times A, and then a semicolon at the end. Again, it complains because we didn't import the types yet, so we're going to do that now. All right. So now we have access to the management canister from within our Motoko project, which is pretty cool already. And like I said, what we are going to talk to is the Coinbase API. And we're going to use an endpoint called, one second, let me open that up here. Whoops. Called get candles. And like also previously mentioned is to make an HTTP outcall, we have to use the HTTP request on the management canister. And now you might be wondering like, okay, but how do I know what arguments I have to pass? You know that from the types that we just generated. So by looking at what this method takes as an input, you can basically, you basically know all you need. And also like the compiler basically like warns you if you do something wrong or if you're missing something. So unless you have like everything right, it probably won't like compile or work. So let's go through those arguments one by one to actually like know what exactly we have to pass. So the first one is the URL. I think that's probably pretty self-explanatory. That's the URL you want to call. The second one is like the method that you want to use, like the HTTP, or not the method, but the request method that you want to use. It's a variant type, so it can either be a get request, a post request, or a head request. Then the next value is a bit more interesting. It's the max response bytes value. And what it does is it actually allows us to set an upper limit for the size of the response from the API that we expect. So what we're trying to do here is that we try to get as close as possible to the real value, but we can never be lower than the real value. If we provide like a smaller max response size, max response bytes value than what the actual response is going to be, then the call is going to fail. And the reason why we want to have a value as low as possible is that we have to pay for that. So yeah, if you don't specify anything, as you can see, it's like optional. It assumes that you want to like use the maximum value, which is 2 megabytes, and that's going to be like pretty expensive probably. All right. So let's take a look at the documentation of our endpoint. So we have to provide a product ID, which is like basically the pair that we want to look at. In our case, it's going to be IC PUSD pair, then we have to provide a start, which is like a timestamp for the starting range of aggregations, and a timestamp for the ending range of aggregations, and then like a granularity. And we actually use like a converter to get a Unix timestamp for a certain date. And the date we are looking at is the 11th of May 2021. So this thing here. So this is start. What was this again? ICP USD. And then the end time, we are going to just increase this by 60. So like one minute more. So this ends up being 607 and the granularity is 60. So we basically look like at a 1 minute like time frame. And that's the data that we're going to get back. And then we can go up here to curl to basically get like a pre-written code snippet that we can just like pass into our terminal to get back the data. And as you can see, that worked. And to get like an understanding of what those values actually represent, the first one is the start time. The second one is the lowest price during the bucket interval. The second one is the highest price during the bucket interval. This one is the opening price, so like the first trade that was made into the interval. The next one is the closing price of the interval, and the last one is the volume within that interval. All right, but that doesn't really tell us like, yeah, like how big this response that we get back down here is. So we're actually like modifying this a little bit, and I already pre-wrote this, so I'm just going to copy paste it. And what this does is that it actually adds like a V flag for verbose. So we have like a little bit more output. And this thing down here gives us the size of the header that we get back, because we also have to, like, for the calculating the max response bytes, we also have to consider the header size. So like the entire response, not only the body, but also the headers. So if you run that again, this last value here is the header size. And up here by standard, we get like an idea of how big the content is. And we actually assume, because this could be a variable in general, but we're just gonna assume that each one of these entries can have 10 bytes maximum. So that would be like 60 bytes. And then we are going to add this on the value down here. So we end up with like roughly 840 or something like that, 850. And to be like conservative, we're actually rounding that value up to 1,000. So we are going to set the max response bytes to 1,000 bytes. All right, let's go back to the interface. So the next thing would be a body. We don't want to send a body, so we're just going to ignore this for now. Then a transform function, which is what I basically talked about previously in the presentation. And then some, we're also ignoring it for now. And then also the headers that you want to set for our request. And for the Coinbase API, you actually have to set a header because it expects a user agent. Otherwise, it will, otherwise it will fail. And if you want to know like how to set the header, you know, like this is like an array of HTTP headers. And if you go up here, we actually see the definition of an HTTP header. It's an object with a value of text and a name of text. So that's how we set the header. So the value would be like user agent, and the name would be whatever you want to set as a user agent. All right. Then what are we going to do next? We're going to actually change the return type here to types.http response, because we want to now actually return an HTTP response instead of text. And then we're also going to make an HTTP call, because it takes too long to write all of that out. Again, I pre-wrote that, and I'm basically just going to copy paste it. But what happens is that we await a call, because it's asynchronous, we have to await it. We store the response from that call into the HTTP response variable. Then we basically provide the URL. We get the URL from this curl command here. We basically just copy paste this. Then we specify the method we want to call or make it like a get request. Then we specify the max response bytes. We just calculated that, and we said we're going to send it to 1K. We don't pass in the body, so we set that to null. We don't care about the transfer function, so we also set that to null. And then we provide the headers, so our user agent, because the API wants that. All right, so that looks good, I guess. So let's deploy this locally. Let's go back into our project, and we're going to run dfx start clean, and also in the background. Clean is a flag for like clearing up any state left over from previous runs of dfx. It's a pretty helpful thing, and if you don't care about like previous state, I always use that just to make sure that I start off blank. And now we are going to deploy. Takes a little while. Okay. Now we're going to access our local Kenneth UI, and we're actually going to call the get price and see what happens. Oh, that looks bad. So our call was rejected. We got like a request ID with that rejection, a reject code, and also a text. This basically said HTTP request sent with 0 cycles, but a couple of million cycles are required. So what this basically tells us is that we don't get this HTTP request feature for free. We actually have to pay for it, and we are paying for it in cycles. Yeah, that's interesting. And the other thing is that we didn't handle an error, and that's why the call was rejected. So what are errors, you might wonder? So when we make a call here, okay, look. Okay, so errors are values that can only be thrown and caught in asynchronous context. And this is typically the body of a shared function or of an asynchronous expression. And the management canister, like this IC thing here, actually throws an error if the call fails. So if we head back to the, oh no, that's another documentation. If we head to the documentation of the HTTP outcall feature, there's actually like a section on errors and debugging, and that lists like the most important errors. And this is our error. And as you can see, the description is at least the required amount of cycles need to be sent with the request in order for it to get fulfilled by the subnet. So to catch that error, because like we actually have like a result type here. So if something fails, we don't want to like just like trap and everything like goes, breaks. We want to like gracefully fail and then return like an error telling the person, hey, something bad happened. And yeah, this is basically like what happened. So to do that, we are actually wrapping this entire call here in a try block. So let's move that in here together with the return. And then wait, is that, no, that has to go down here. And then here we need a catch. And what we do down here is that we, if something happens, like if we catch an asynchronous error, we are going to return an error instead of an OK, and we are going to say reject message, and then we are going to provide the actual error message. And we can extract that message from the error by using the base library error and by calling the function message on the error. So it complains again because we did not import error yet. And this has 1R too much. Okay, so now we basically fixed the first issue. Now we are actually catching asynchronous errors, which is good. So if you were to deploy this again, and then call that method again, we shouldn't get like a reject. We should get like an error with that reject in it. Yeah, as you can see now, we actually get back what we expected, a variant, and the error variant that basically tells us the reason for the rejection. All right, but now we still have to send some cycles to the management canister to actually get it to fulfill our HTTP request. All right, so what we have to do is we have to preload each call to each HTTP request with cycles to pay for the computation. And yeah, but like the first question obviously is like, how many cycles do I have to pay? Like, how do I know how much cycles I have to send? And therefore, again, we consult the documentation. There's a pricing section down here. It basically gives you a formula on how to calculate the amount of cycles you have to send. As you can see, it's important how many headers you send. Like this name basically refers to the size, the byte size of the name, and the same for the value. Also, the URL we are calling is important. We have to consider that. The length of the name of the transform function, the transform context, body length, and so on and so on. So basically what you pay for is everything variable in that response. Because if I have like a huge header, each replica kind of has to work with that header, and to make it fair, because apparently like they have to somehow make more computation if this variable size is bigger, we have to pay for it. Another thing is the scaling factor, which considers the subnet size. We are on an application subnet, so our subnet size is 13, so we can just ignore that. And then in the end, you just basically have a base fee of 400 million. You take the request size and the max response size, multiply that with 100K, and then you have your output. So, I mean, I can quickly show you the calculation. This is what I did. So the outcome is 530 million and 700,000. You can recalculate that yourself if you want. And as you can see, it's actually exactly what the management canister tells us we have to send it. We have to send to it. So the math seems to work out in this call. And so when you send cycles to the management canister, you basically have to send enough cycles to cover that cost, but you can also send like more cycles because excessive cycles are returned back to the caller. But to be as efficient as possible, we actually sending the exact amount of cycles. And now obviously the next question is like, how are we going to send cycles? And to send cycles, we're going to use a library called experimental cycles base library. It's part of the base library. And that is marked as experimental because it might change for future versions of Motoko. So be aware of that. And what can happen with cycles is that they can be transferred between canisters and sent and received from messages. So that is basically shared function calls. And a caller can choose to transfer cycles with a call, and a callee can choose to accept cycles that are made available by the caller. And this transfer of cycles has to be made explicit, and the callee can then basically accept some, none, or all of the available cycles that are transferred with the message. And the remaining cycles, if it accepts none or only part of it, are returned to the caller, like I said. All right, so we are going to use the experimental cycles library. And there's a method in there that's called add, which basically adds cycles to the next shared function call. So if I would have put in the statement after the call, again, we would have had an error because I pre-charge, I say like next call, send this many cycles, and then I make the call. So what was it? 530,700,000. All right, I think that looks good. Let's deploy this again. And let's call this method again and see if that works. How many cycles did I send that? Oh, I'm missing a 0. It seems. Yep. Thank you. Thank you, candidate interface. So we redeploy this. Oops. And now we make the call again. And yeah, congratulations. That worked. So we just made our first HTTP out call, which is pretty nice. But there's like one weird thing. As you can see, the body looks like weird. Like, why are those like numbers there? I was expecting like an array of arrays that basically contain like my historical price information. So why does it look that weird? And to get an answer to that question, we basically go back to our interface, to our Canvas interface, and we can see that HTTP request returns an HTTP response. And if you go up and check what that response looks like, you can actually see that the body is encoded as an array of net8s. So what we are going to do next is we are going to transfer like the byte values of the text back into the text. And for that, I first define a new type, which is basically the same as this, except that the body is of type text and not net8 anymore. So let's do this. I just copied this. And then the next thing I'm going to do is that I create a new file that I call helpers.mo. And in there, I basically, somehow like when you auto format, it adds this comma and then it's apparently like not valid anymore. So I have to be aware of that. And I also like, I create a function now that's called decode body that basically takes an HTTP response and returns an decoded HTTP response. So it transforms the body part of the HTTP response from a vector of net8s into text. And because it takes so long to write this out, I prepared this. So this is the method. If you're interested, you can dig into that later on. I will share the guide that I'm currently following, and it's all written in there. All right. What we do next is that we actually pass the HTTP response to the decode body method. And that doesn't work because I haven't imported it yet, which I'm going to do now. All right, and now it complains because it says, something's like off, because previously I was returning HTTP response, but now that's not an HTTP response anymore. That's a decoded HTTP response. So I have to check change my return type as well. So with that out of the way, let's redeploy and check if we can actually see text now. This is basically like a warning that the interface changed, but that's fine. Because we are like still in development mode, and no one is consuming that interface of our canister. And as you can see, that worked. I basically now have the exact same response as the one I received from my direct call to, I don't know, like how to position this, but if you like go over the values, you see that they are the same as they should be. All right, cool. So obviously we have to deploy this to mainnet as well. I mean, like if it works locally, after all, our local replica mimics the production network, so this should just work out of the gate. Network, I see. All right, so it's deploying this now. I'm very sorry for taking longer than expected. I hope it's fine. All right, so let's go and check that same canister on the mainnet and call that get price method again. What do you expect it to happen? First of all, it takes longer, obviously. But second of all, we receive another error. Reject message So the management canister trapped again, but because we have our try catch block, we catch that error, that asynchronous error, we extracted the error message and we display it here. And the error message is canister HTTP responses were different across replicas and no consensus was reached. So that sounds bad. Why did it work locally, but now all of a sudden the replicas can't reach consensus anymore? And the reason for that is because locally you only run one single node, so one replica. And obviously, if there's no other replica that receives like a different response, there's no problem reaching consensus, because if you're alone, you're basically dictating what this response should look like. But on the subnet that we deploy to, we have different nodes. Now we have 13 different nodes. They all call the Coinbase API, and apparently they all received something different back from the Coinbase API. And yeah, let's take this graphic back into consideration. So yeah, so if we look back to the presentation, we see that there was like a restriction, and the restriction was that the responses must be similar, and that we have to provide a transform method that is applied to each of the responses from the replicas, so that they are in the end all the same. And when they are passed to the consensus layer, that the replicas can actually reach consensus on the responses. And apparently, we now have to use this transform function to transform the response we receive from the Coinbase API in a way that all replicas can then agree that yeah, they all have the same response. And yeah, to do that, we first have to like see what are the variable parts in our response. So when I call this again with the verbose flag, I can actually check like the headers for any weird thing. So the first thing we see here is the date field. That could be different from node to node, because like I mentioned earlier, maybe one node is in Asia, the other node is in Europe, but the server that we want to call is in Europe. So Europe calls it like at 0.914, and Asia maybe calls it at 914.3 or something like that, or 1. Another thing is, for example, this E tag here, this looks like it could change from call to call. And then also this Cloudflare identifier is probably changing from call to call, like from replica to replica. So because we don't really care about those headers at all, like I don't need them. The only thing I'm interested in is like this data down here, and that should be the same for everyone, because we are requesting a very specific time frame on the Coinbase API, and that's the data that Coinbase returns should always be the same, because I always ask for the same time frame and the same data. So what are we going to do? We are going to add this transform function to our replica, to our code. And again, if you're wondering like, yeah, but what does the transform function look like? We go back to the interface definition, and we see that transform is actually an object that contains a transform function, basically, and also context. And the context allows us to parameterize the transformation on a per request base. But for our case, we don't really need the context, so we ignore it for now. And yeah, the next one is the transform function. And the transform function has to be a shared query. And that means it has to be part of the interface specification of our own canister. So we're not defining this in helper somewhere. We are defining this here in our public interface. And the reason for that is that the replicas actually call the transform function on our canister, passing it the HTTP response and receiving back the transformed HTTP response. And if we wouldn't like expose this method on our canisters, there wouldn't be any way for the replicas to actually call it. All right. Also, for the sake of time, I'm just copy pasting this now because we're like already like late. So this is what happens. It yeah, basically it takes a context, it takes a response, and what it does then, it doesn't do anything with the context, it just returns the response and it sets the headers to an empty array. So it removes all the headers from the response. Quint talked about the syntax. That's pretty new and pretty handy. And so we keep everything in the HTTP response the same, except headers, set it to the empty array. All right, now let's add this to our transform function. Like I said, it's an object. And the function is basically the transform function, transform. And our context, oh no, that's not an, what's it equal? And our context is just like the empty array. So what's wrong here? Here it's not an optional. So I have to add the question mark. Because yeah, this one is an optional. All right. One thing changed now. Basically, if you remember how we calculated the cost for the call, the byte size of the name of the transform function was also considered into the calculation. So we have to recalculate the amount of cycles we have to send. I already did that, and it's changing a little bit. So this should be the new amount of cycles that we have to send. So with that, everything should work. So we are going to redeploy this to mainnet. And we're going to go back, reload that page just to be sure. Now we see that we actually exposed this transform method. Oh, sorry. Let's call get price. And as you can see, it worked. And yeah, that's basically it. So congratulations, we just made our first HTTP outcall on mainnet. And we basically, yeah, solved everything. So I would say we go for another Q&A now. If there's interest, I'm going to do the next lecture as well. So
Yeah, feel free to take time. There's no rush, and you've got the next lecture anyway. So yeah, you have until you need to start prepping for the next lecture.
okay, I'm going through the questions asked in the Q&A first. Lee asked, where can I get a candidate file for all running canisters? Canlister used to do this, but now does not allow me anymore. So I think Canlister still allows this. I will share my screen and we will investigate together. Fun fact, I actually helped building Canlister together with another community organizer. So let's, for example, take just our canister that we deployed on mainnet just now and see what happens. I mean, I didn't do anything, but I can just like look at the candidate straight away. So you could see like the get price method here, the transform method here, and you can also view the entire candidate file and just copy it. But if you don't need the candidate file and you basically want to go to Motoko directly, you can go on Motoko and basically copy the description directly. So yeah, that works. Look for internet identity, please. Yeah, so like for Canlister to actually infer the type of a canister, or like the interface description of a canister, what Motoko canisters do is that I think this recently changed. I think there's like a special section in the WASM file where they like store the interface description. And I like previously Motoko did this automatically, like just in general, like storing the interface description, but for canisters written in Rust, this didn't happen automatically, and people would basically manually say that they want to do this. So I guess if you say look for internet identity, I guess that maybe I should add identity. I guess that this is not the case for that canister. I mean, it looks like it's present. I don't know. I didn't test it yet, so I don't know if it's a correct interface, but it's there at least. So yeah, if you, yeah, I think that answered the question. If not, just okay, great. Lee just said apparently it's just him who can't access it. So yeah, maybe try a different browser or something. I don't know. Okay, so sometimes the video quality drops briefly. Is this on my end or does everyone have this issue? Could be on our end. I don't know. So we're like at the moment not that many people, but sometimes we are like 20 people in one room and there's like a whole co-working space above us, and so we are all in that Wi-Fi. So it could be that sometimes there are like some problems there. Lee also asked, why do you use the value exchange rate canister? So I use the value exchange rate canister in my headers for the user agent. To be honest, I realized that it has exchange rate canister because I inspired myself from the exchange rate canister example. So basically, I just copied the header for that. And then when I wanted to change it to price feed canister, I realized that the length of that header would be different then, and then I would need to recalculate all those cycles again, and I was too lazy to do that, so I just kept it as exchange rate canister instead. What's a shared, Atia asked, what's a shared query? What's the difference with a public query func? That's basically the same thing. Just like in type, if you want to like specify the type for such a function, it's called like shared because you share it with other canisters or people. I think you can actually also do like public shared query func. So yeah, but you can also omit it. So I'm too lazy to type it, so just like omit it. All right, let's see if someone raised his hand. Anyone has any more questions? Okay, then thank you for asking questions and for sticking with me for almost 1.5 hours. I will be putting this on GitHub. Yes, that's a good idea. But probably not right now. Throughout the day, I will put it on GitHub, and I will also, like at the end of my slide decks, if you go down all to the end, there's like a live coding thingy, and if you click that, you actually go to the public page of basically the guide. If you want to follow along, if you want to redo this, it contains basically everything that I just said. And there in the beginning, I will also add like a link to the GitHub repository once I deployed it. On GitHub, or once I uploaded it to GitHub. Okay, and Anonymous asked, what about data points per API and max response bytes? Maybe you want to raise your hand, because I don't like max response bytes. I think I covered it in the lecture, but I don't know what data points per API refers to. So yeah, maybe you can clarify. You can also just basically write it in the Q&A thing if you don't want to talk. Data points per API. Maybe you are referring to Yeah, I don't know. I'm sorry. I'm not sure what you mean. But you can, I don't know, tag me on Discord and I will try to answer it. All right. Then see you soon, guys. Bye-bye. Do I just pause the recording or do I end the meeting or like what?
You just send the meeting.
Okay.